So the previous video was this free lunch for few short learning distribution calibration, and in this we already have seen somewhat concept of few short learning. What is few short learning? You have last number of example, and out of that last number of example you have to train a model, you have to learn distribution. So because of last example you'll have a problem of overfitting, so that's why this paper, free lunch for few short learning paper, have proposed something like propose a simple and distributed calibration technology, and also so the complete paper is based on estimation of uh, truth ground truth related distribution using one example, and then a classifier train over that. So that these concepts we have seen and how they have done, that we have seen. So whatever you have seen in this paper and in this strategy, because this paper have working on the concept of this mean and variance and Gaussian distribution, right? So this paper and this paper, so this paper was free lunch for few short learning distribution calibration, and we have seen some uh, thing like in this paper they have assumed every dimension the feature representation follows a Gaussian distribution, so that the mean and the variance of the distribution can follow sorry can borrow from that the similar classes whose statics are estimated by adequate number of samples. So I don't think uh, let's say, and so this paper we have seen, but one more thing I get to know that in this paper also related to bridging the gap between this paper bridging the gap between few short and many short learning via distribution calibration. So if you see this complete paper, free lunch paper, and this distribution calibration paper, so see heading is different: free lunch for few short learning distribution calibration, and this is bridging the gap between for between bridging the gap between few short and many short learning via distribution uh, distribution calibration. So all the things like you can see from here, abstract is similar, introduction is similar, abstract is somewhat similar, and exact copy and paste things are there. And here also after this introduction you'll see this diagram. Here also you will get to know about this diagram. So this diagram is also copy paste diagram, and main approach. So the main approach is also similar to this paper, and main approach uh, here is its main approach. So algorithm also similar, statics of base classes is also similar. So just telling that the main problem is exactly similar, but after that things what this paper have done, and what is the what difference this paper made is generalization error bound. So in this sense we can say generalization error bound, we can say this paper is different from this free lunch distribution calibration, right? So what is happening here, because for till this section 4 you can go to my this video and you'll get everything there. And after that this is extension of this paper, because this paper is also written by us, I think same author. Let me check again. Xiu Yang Li Lu Liu Minju. Su Yang Li Liu. Shu Yang, yeah, he's same author, and these are different authors. Okay, so the main author is Su Yang. So this paper and another second paper, both paper are published by Su Yang with their supportive team, right? So this is extension of this paper, and in this paper, uh, the main concept that differ is about generalization error bound. So we can see here this generalization error bound, because they have discussed about expected and empirical risk of a classifier can be defined as. So here what they are doing, they are just traditionally minimizing risk minimization, they are doing. So we know that how to do this risk minimization. So as we're using this concept of expected and empirical risk. So this is let's say expected risk, and this is empirical risk. And this symbol, this n, capital N is size of this capital N is size of training sample drawn from the distribution D, and in the case of few short classification tasks, the distribution of generated set, supported set, and the query set are denoted by DG, TS, and DG respectively. And the classifier after is learned from the support set S and the generated set G. So here support set and generated set. Ah, right. And so the finally the generalization error is defined as in the sense of this, and then we have this rg after bar and r bar s plus f is equal to this. And where r dash and r bar are aspect empirical risk, and is the distribution of and that D, distribution D. So in this paper, they bound the generalization error by employing Rademacher complexity, which is one of the most frequently used complexity measures of function classes. So it can be used to derive data independent upper bound on the learnability of function classes, and intuitively the function class with smaller Rademacher complexity. So they are here discussing about Rademacher complexity, and they are saying that Rademacher complexity is easier to learn. So yes, I think it is also easier to learn. So let's see what is this Rademacher complexity. Let's according to definition of this, let's f be a function class, and z and n equals to 1 to n be a sample drawn from z denotes sigma n equals to 1 to n be a set of random variables independently taking either value from -1 and 1 with equal probability. Then the rad match complexity of f with respect to the sample is defined as that. Okay, so this is Rademacher complexity of f. And what is f? F, we have function class. Okay, so Rademacher complexity become this. And for the first two term in the right part of equation 13, where is equation 13, first two part. Okay, so this is explanation. So for the first two terms in the right part of equation 13, uh, since equarian support set both sampled from the novel set, then the distribution and thereby the expected risk are the same. So here they are saying okay, so here right, so this left side and right, this is left and this is right side, so they are talking about these equations. So they are saying for the first two terms in the right part of equation 13, since the query and support set are both sampled from the novel set, the distribution and thereby the expected risk are the same. So and uh, that means same means this query and support, this query and this support should be equal to, if we reduce this, because yes, because here you can see that. So what they are saying that this thing is query and support set are both sampled from the novel set. The distribution and the aspected risk are the same. So this aspected risk are same for the next two terms in the right part of equation. The gap between the gap means this R support of f and R support plus query of yes of function is caused by distribution shift. So they have leveraged a calibrated Gaussian distribution to approximate the assumed Gaussian distribution, and thereby the to distribution of the support novel set, and thus there exists a distribution shift error consisting of distribution assumptions error and a distribution approximation error. Okay, so here empirically, for r of s plus g given a tau e belongs to 0 comma 1, we consider the convex combination of the support risk and the generated risk. So this is a support risk and generated risk, and they have taken as a convex combination of this support risk and generated risk. So as discussed before, setting a tau introduces a trade-off. Discussed before means in these two paper, tau introduces a trade-off between support set and that is reliable but not sufficient, and the generated set that is sufficient but not reliable. So let's say setting a tau equals to 0.5 means that we treat the generated as equally as support set. So then based on this 36 equation, assume that the neural network has d layers with parameters matrix w1 to wd, and the activation function sigma 1 to up to sigma d minus 1, and let's just continue satisfying sigma j 0 is equal to 0, we denote by h such that x implies wd sigma d minus 1. So this is a bit complex equation to understand, and the standard form of the neural network h is equals to, and this arg max I belongs to I 1 to c h of I. Then the output of the softmax function is defined as fi x is equals to e exponential of this hi x given this sigma j equals to 1 to c exp of h j x I is equal to 1 to this can be bounded as follows. So one more theorem they have given in this. So I think first was definition, and theorem is assume that f is a function class consisting of function with a range of a comma b let z1 and s is equals to z and s, and n equals to 1 to ns, and n1 and g is equals to zn, n equals to 1 to ng be two sets of independent and identical distribution samples drawn from the support or novel domain ZS and the generated calibrated domain ZG respectively. So the Frobenius norm of the weight matrix W1 to WD are at most M1 to MD. So let the activation function be one elliptic positive homogeneous and applied element wise such as ReLU. So here some mathematical task they have done, just complex time to understand. So this so what total difference is about this section, this fourth section they have included in this paper, and other things completely similar, no difference, nothing, everything is similar, and Here also these things are also similar, and yes, so here they have shown some differences between those classes, and here also they have included something like estimation error things they have included, because in this paper there wasn't estimation after main approach there wasn't estimation error. So yeah, implementation details. Yes, so this paper was about that, and some more experiment they have included, like in the previous paper there was some experiment, and where is that is those experiment. So these are another experiments before that. So I think these tables would be similar. Optimization base, no optimization base, where is that table? Yeah, this table. So these both tables would be equal, and anything change? Yes. So here these three tech methods they have discussed about their methods, but here they are saying that their method so these methods are also similar now, 0.41, but after applying that accuracy improved up to some limit. So yeah, so there been some improvement here also. So you can see this paper is extension, and also lot of proofs they have given in this paper, proof of theorems, and this theorems proof of theorems will take some time to understand because this is mathematical. So I request that I would suggest that you should go to these things and try to understand these equations, because these equations and of generalization of error make this paper different from this free lunch paper, right? So okay, so that's it for today, and next video we'll see something new, and some further improvement, maybe some further improvement or some new lecture. Okay, bye.